We've talked before about quadrilaterals. A quadrilateral is a four-sided polygon. Within that group of quadrilaterals, there are several special kinds, one of which is a parallelogram. So by definition, a parallelogram is a quadrilateral with both pairs of opposite sides parallel. That's why we call it a parallelogram. And so that's the definition of a parallelogram, that the opposite sides, both pairs of opposite sides are parallel. But beyond that definition, there's also several other things that can be easily proven that will always be true about parallelograms. And we're going to learn about some of those in this video. So to start off with, the theorem 5-1, it says that opposite sides of a parallelogram are congruent. And let's prove that real quick. So the given information is just that you have this parallelogram here, EFGH. Now we know that by the definition, these opposite sides are going to be parallel. So I'll go ahead and mark that. And my job is to prove that EF is congruent to HG and that FG is congruent to EH. And I'm going to go ahead and prove this, but I'm not going to do it as a two-column proof. I'm going to do it more as kind of like a paragraph proof. And the first thing I'm going to do is I am going to add in what's called an auxiliary line. I'm going to connect vertex E to vertex G. I'm going to draw one of the diagonals of my parallelogram. And if I do that, then I'll notice that I would have two triangles. And these two triangles are going to be congruent to each other. Why are they congruent? Well, I have the reflexive property for segment EG congruent to itself. That's one pair of sides between the two triangles. I have a pair of alternate interior angles there that are congruent because those opposite sides of my parallelogram are parallel, so those alternate interior angles will be congruent. I would also have these alternate interior angles congruent, and that would mean that the triangles would be congruent by angle, side, angle, and then by CPCTC, these pairs of corresponding parts would be congruent. So let's go ahead and write that out. First I'll say, first add auxiliary segment or line EG. Triangle EFG is now congruent to triangle GHE by angle, side, angle. And then in parentheses I'll say that EG is congruent to itself, pretty self-explanatory by the reflexive property. Angle FEG is congruent to angle HGE, FEG congruent to HEG, and angle HEG is congruent to angle FGE by alternate interior angles. Therefore, EF is congruent to HG and EH is congruent to FG by CPCTC. So there's a proof. It's more of a paragraph style proof, not a two-column proof, but it gets the job done. It explains that by drawing that auxiliary segment EG, we have two congruent triangles by ASA, and then by CPCTC, we can prove that the opposite sides of any parallelogram will always be congruent. Well, what else could we prove? In theorem 5-2, we have something that says that the opposite angles of a parallelogram are congruent. So if I have this parallelogram here, it would mean that this angle and this angle would be congruent to each other, and that this angle and that angle would be congruent to each other. And you can see actually the proof, if I wanted to do a proof of this, it would be pretty similar. I would add in an auxiliary line, I would show that the two triangles are congruent, and then these angles would be congruent parts of corresponding parts of congruent triangles. In theorem 5-3, we can say that the diagonals of a parallelogram bisect each other. So if I were to add in the diagonals of this parallelogram here on the right, diagonals connect non-consecutive vertices. So in any quadrilateral, you'll be able to draw two diagonals. What we now know is, let's see, let's put some letters, let's put some labels in here. If we call this parallelogram ABCD, and then this point right here where the diagonals intersect are E, we would know that AE is going to be congruent to CE, and that BE would be congruent to DE. And there's a proof of that would use corresponding triangles too. And using, we could look at proving that these two triangles are congruent, ABE and DEC, or that triangle AED is congruent to triangle BEC. There's a couple different ways we could do it, but we'd use corresponding triangles to prove that these diagonals end up bisecting each other because these pairs of segments are congruent. But that'll always happen in any parallelogram. So let's look at a couple, let's look at some always, sometimes, or never questions real quick. A parallelogram is always a quadrilateral, right? That is part of the definition of a parallelogram. It is a quadrilateral where both pairs of opposite sides are parallel. So it's always a quadrilateral. But a quadrilateral is not always a parallelogram, right? Some quadrilaterals are parallelograms, but some are not. Some are four-sided shapes where the opposite sides are not parallel. So we have to say sometimes here. Sometimes. All the angles of a parallelogram are always congruent, sometimes congruent, or never congruent. All the angles, right? Well, we know that opposite angles will be congruent. And we know that since it's a quadrilateral, all of the angles add up to 360, right? Because all the interior angles of any quadrilateral add up to 360. So you could look at maybe in a quadrilateral like what we have in this example 2 down here. Obviously, I have two obtuse angles and two acute angles in this parallelogram. But what if they were all 90, right? Because 360 divided by 4 could make 4 90-degree angles. In that case, all the angles would be the same, and we could say that sometimes all the angles are congruent. And just for kind of, a little bit of a look ahead, those quadrilaterals where all the angles are congruent, those are called rectangles, and you probably knew that already. The consecutive angles of a parallelogram. So consecutive angles, if I were to just kind of sketch out a parallelogram over here, and if I numbered those angles, let's say I numbered them 1, 2, 3, and 4. Consecutive angles would be angles that come one right after the other as I kind of move around my parallelogram. So 1 and 2 are consecutive, 3 and 4, 2 and 3 are consecutive, and 3 and 4, and 4 and 1. Those are pairs of consecutive angles. Well, it's asking about whether or not they're complementary to each other. Well, if this is a parallelogram, I know that I have some parallel lines, right? And I know that each one of those pairs that I just named, 1 and 2, 2 and 3, 3 and 4, 4 and 1, they actually form same side interior angles for those parallel lines. And we know that when lines are parallel, same side interior angles are always supplementary, which means they add up to 180. So we can say here they're never going to be complementary. They'll never add up to 90. What they'll do is they will always add up to 180. Lastly, we have part E. All the sides of a parallelogram are congruent. That, as you can probably guess, is sometimes true, but obviously not always. We can see a parallelogram down here where there's clearly two sides that are longer than the other two sides. But it could be possible that we could have a parallelogram where all the sides are the same length, and those are called rhombuses, and we'll learn a little bit more about them a little bit later on. Down here we have an example where it's asking us to determine whether the given pairs of angles must be congruent. So, angle BAC and CDB, BAC and CDB. Maybe it'd be easier to kind of go through and look at, well, which angles do we know would be congruent? And then we can kind of decide if these given pairs are marked congruent on our picture. So we know that the opposite angles would be congruent. So I'll mark these congruent and these congruent. I know I'd have some vertical angles that are congruent, right? I'm going to start running out of markings here. And I know since the opposite sides are parallel, I'm going to have some alternate interiors that are congruent. So I'll just use maybe different colors to try and visualize these pairs that are going to be congruent to each other. So I would have those alternate interior angles congruent. Of course, I could also come over here and do something similar. Let's see, let's mark this congruent to this, And let's find a color we haven't used yet. We can mark this congruent to this. So now, let's see. Are angles BAC and CDB congruent? Yep, that's these two angles marked in blue right here. So I know that those have to be congruent because they're opposite angles in my parallelogram. Angle BAE, so that looks like this kind of neon colored angle. Is it congruent to CDE? Yep, because those are alternate interior angles where the lines are parallel. So we can say yes there. Angle ABD and BDC. So that would be this angle and this angle. Those are consecutive angles, which we know are not always going to be congruent. Maybe sometimes they will be, but not always. Must they be congruent? No, not in this case. Angle ACE, so it's this purple angle that I've marked here, congruent to angle EBD, this other purple angle. We know those are going to be congruent because they're alternate interior angles and the lines are parallel. Angle CAE, so that would be this pinkish line here, and EAB, which is this chartreuse angle right here. So are these two always going to be congruent? No. Maybe sometimes they are, but not always. So we have to say no, they don't necessarily have to be congruent. Angle CEA and angle DEB, that's a pair of vertical angles, so we know that they would always be congruent. So there we have our examples, or our answers for example 2. Lastly, let's look at what we can do with some algebra and some of these ideas about what has to be true in a parallelogram. Let's find the value of each variable in these two exercises. First of all, let's look at x right here. I know I have a 5x over here for angle C and an 80 degrees over here for angle B. And I know those two must be congruent to each other. So I can say that 5x needs to equal 80, in which case x would be equal to 18. Divide both sides by 5. Now what about y? It doesn't have anything over here. So I can't use this idea that opposite angles would be congruent, can I? Because I don't have anything to set y equal to. But what I do know is that these two consecutive angles, angle A and angle B, they have to be supplementary, right? I know that y plus 80 has to give me 180. So if I subtract 80 from both sides, I know that y has to equal 100. For A, I know that segment BD and segment AC would be congruent because they're opposite sides of my parallelogram. So that makes A pretty easy. It's going to be equal to 6. And then I know that AB and CD would be congruent to each other. So to find B, I can take 3B minus 2 and say it should equal B plus 6. Sorry, my B and 6 look almost identical there. That's a B. Let's go ahead and subtract that B off of both sides. 2B minus 2 equals 6. Add 2 to both sides. 2B equals 8, which means that B would equal 4. Over here on example B, again I have A right here. Segment CD has a length of A, and segment AB has a length of 12. So I know that A equals 12 because those opposite sides should be congruent to each other. I have B involved in segment AE, and I know that those diagonals would cut each other in half. So I could say that 3B minus 2 would need to equal 7 right there. So if I add 2 to both sides, I would know that 3B equals 9. So B equals 3. To find X, well, let's see here. I got an X here, I got 5X for angle ACD, but I don't have anything over here for the opposite angle, angle ABD, so I can't go that route. But what I do know is that angle CDB has a measure of 80, because 45 plus 35 gives me 80. So I could say that 5X plus 80 should equal 180, because those consecutive angles need to be supplementary. So that means that 5X equals 100, and X must equal 20. And lastly, I have angle Y right here. I know that since these opposite sides are parallel, by alternate interior angles, those two angles should be congruent. So Y would equal 45.